No, it's fine. I'll see someone yeah, no, because I can't see. No.
Except for
So,
Okay, welcome everybody. Before this afternoon's talk, a quick announcement about the dinner tonight. So we have this crayfish dinner. It will start around 6:30 and it's in the other building, the physics building. So please all join for that dinner. But before that, Ms. Milovanovic, who will talk about wave functions, superfluid disorder, quantum Hall bilayers.
Yes, that's the title of my talk. So let's introduce the quantum Hall bilayer. We have two-dimensional electron gases, strong perpendicular magnetic field, and there is, I will denote by D, the distance between layers. In experiments, it's the density in the layers that we change, adjust the magnetic field and make the distance, effective distance between the layers is changing. So in each layer, each electron sees two flux quantum. But that flux quantum is shared by, these two flux quanta are shared by electrons. So you have 1 and 2 second layer, so second electron, so total filling factor is 1. Now, I want to emphasize at the beginning of my talk to tell you that the quantum Hall bilayer concerns or realizes this fundamental problem of superfluid disordering in 2+1 dimensions. So it might be like advertisement or advertisement, let's speak American, or some overstatement, but I just want to notice that if the distance, as you know, as the distance between layers is small, you have a superfluid. As you increase the distance, that features of your superfluid decrease, and you disorder your superfluid. So what is special about quantum Hall setting? Well, we can kind of say to other condensed matter people that we have wave functions, field theories, numerics, and experiments. The order depends on you, what you find the most important. So the content of my slides. The first part introducing and discussing two possible families of the wave functions for the quantum Hall layer that will represent two ways to disorder superfluid. And arguments can be given that somehow these two ways corresponds to two paradigms that we know of disordering the superfluid. One is Berezinski-Kosterlitz-Thouless, vortex anti-vortex pairs, or the second, so it's 2D XY model, or something that probably is 3D XY model, something that needs time direction to be described in the proper manner. But we will not dwell on that. In fact, during this talk, we will just consider superfluid disordering on the level of the phonon contribution. So the most simple quantum fluctuations that you can have. Every superfluid has Goldstone, every good superfluid, long-range ordered, has this Goldstone mode, so phonons, and they're described, they're harmonic oscillations, and they can execute zero-point motion. So that's the phonon contribution that I'm talking about. And we will see how these two possible families incorporate this phonon contribution. And at the end, some comments what can be outcome of the superfluid disordering. That will be some kind of paired phase. So the first part, so one, well, I'm saying two families, but at the beginning of all, we have other two extremes of the quantum Hall bilayer. Either layers are close to each other, or very at large distance there is between them. And the first thing that we know, and from experimental and theoretical point of view, we know rather well that the good trial wave function for this case is so-called 1-1-1 state. So this is just a simple generalization. We are at total filling factor 1. This is simple generalization to two species, two-layer indices, that Z's and W's. And so when you fix Z, your electron, that's also zero, not for all other, but also for W's. So correlation Hall is just opposite the electron. And so you have a case for some exciton binding, but somehow you contain your boson. But that's not enough in the sense what is really characteristic of this wave function, that you can somehow, you have freedom to transfer some Z's into W's, and basically you stay with the same kind of wave function and of the same energy, because, as I probably didn't emphasize, when the distance is small, inter and intra Coulomb interaction is about the same. So this is your good ground state. So it so somehow this description just wants to motivate the short note that this wave function describes superfluid, excitonic superfluid, and that was described theoretically, experimentally. And appropriate quasi-particles in this case are excitons, which in our language of quantum Hall we call composite bosons, the oldest composite particles that we know for description of the quantum Hall states. Now, when the distance between layers is large, we have two decoupled layers, and we know what is the physics of 1/2 in the lowest Landau level. That's Fermi-liquid-like state. So here is the Jastrow-Lapin factor. We have to accommodate the plane waves because of anti-symmetrization. So somehow the most important feature is that this power is to the second. That's the power that are bound to have quasi-particles to be so-called composite fermions, the usual quasi-particles of the quantum Hall description of our quantum Hall states, and so that's what we know very well. Now we want to address the intermediate distances. So we have these two extremes, and now we want to address some d of the order of the magnetic length. So one way to approach the problem is to say, well, classically speaking, in the upper layer, I will divide my electrons to those that correlate as composite bosons, and some of them will correlate as composite fermions. And I will anti-symmetrize after all. These are down layer electrons. And this is to represent 111 wave function of these composite bosons. So intercorrelated state. So certainly I will do overall anti-symmetrization, but once I assume this mixed state picture, there are two remarks I want to tell you. First of all, it's a trivial one. You imagine as you increase the distance, you have more composite fermions than composite bosons. You transfer some composite bosons to composite fermions, transform. And the second thing, very important, is that we need some intercorrelations between these condensates. Why? Even when you study your Laplace wave function on the disk, you know the maximum power should be of any coordinate should be equal to the number of flux quanta through the system. So in our case, that any coordinate here or here or here should fulfill this condition that this power in the thermodynamic limit is equal to the number of electrons, because we are in the at the total filling factor 1. And given that, I need to have some intercorrelations to increase the power of these condensates. So let's, if I have two groups, let's A and B, I insert this Jastrow-Laflin factor in this manner, and I will denote by a line this Jastrow-Laflin factor. So what you end up really is two possibilities to insert these factors. Either you will do in the way of the 1-1 state, where you will be connecting almost everybody with everybody, or you will intercorrelate exclusively inside the layers. So much more in the spirit, of the decoupled layers. So, so these are A and B are simply the basic configurations that you can have, intercorrelations that you can have, and let's just count powers for the case A. So if I have number of flux quantum highest power of my bosons with layer index sigma, certainly I have number of bosons of the same layer, number of bosons of the opposite layer, number of fermions in the same layer, number of fermions in the opposite layer. Well, what our fermionic coordinates do, I have, you see, I have these intercorrelations that gives me the number of bosons of the same layer index, number of bosons, so the opposite layer index plus 2, and that should be somehow written at the beginning. This is interlayer power that we have in this condensate. So it comes from the other fermions in the condensates, and as you remember, that's the power 2. So these are countings in the thermodynamic limit. So these 4 things, or 2, just 2, should be the same. And equal to the number of electrons, total number of electrons. So as you can notice, somehow I have to somehow constrain that the number of up fermions is equal to number of down fermions, just from equating this. But with respect to bosons count, it's up to me to, put more or less whatever I can rearrangement do for the bosons. So in the sense, because of 1-1 nature of the correlations, in this case A, I still have freedom to take some bosons from upper to down layer or down to upper layer, and essentially stay in the same state, and certainly for small distance of the same energy as the beginning state. So this can describe my superfluid. This is something, in the picture that I'm describing you, it's that I'm fixing the relative number between electrons in the upper and lower layer. In the more, I would say, the proper picture of describing the superfluid, you would just need to superpose various relative numbers of these states with different relative number of the electrons, and have some phase fixed as usual in the proper description of superfluid. But anyways, I think in this way, in case B, you end up with the conclusion, as you do this power counting, that number of upper bosons should be the same as number of the lower layers. So the case A can describe the superfluid, but there is interesting additional thing you can do, and that's the pairing between your composite fermions. And as time go on and I tell you more, you will see that it's really indispensable that you include pairing, and to really to have a good superfluid description. So basically, these are 2 families I was talking about. The first family that describes this ordering, and the second family with the pairing. So this is the second part. We just switched to some theoretical things, not very hard in the sense. We just want to describe superfluid disordering. We just want to describe what we mean by phonon contribution to the wave function. So basic Lagrangian for the description of your liquid state is just quadratic in currents and densities. So if I introduce the conservation law and impose longitudinal excitations, ask for longitudinal excitations, I end up with something which is sum of k over k as a momentum of some harmonic oscillators, where these are coordinates and this is my momentum. And so as as a consequence of this, in this hydrodynamic approach, we can easily see that based on these first principles, conservation law and the basic description of the superfluid, of the Goldstone model of the superfluid, we introduce this phonon contribution to the ground state wave function. Each exponential is just Gaussian of your fixed K harmonic oscillator that describes the phonon mode and vector K. And these are fixed things. You can hardly do anything. You in the, well, depends on your interaction, but basically you have this for the Coulomb interaction or any simple kind of interaction. But you can go to Chern-Simons description. That will tell you the same thing, just that of your quantum Hall state, and you will multiply your 111 state with this phonon contribution. In our case, this VK interaction is just the difference between interaction in the same layer, intra and inter-interaction, Coulomb interaction, whatever interaction are they. But rho K is just the difference. We are describing the neutral channel, so it's the difference between ups and downs. So, so for D small and for Coulomb interaction, you can see that this correction is just proportional to D, and so for small d, you just have the possibility of just expanding, and we will call this first term, first correction to 1-1 state as a first phonon correction. So, but let's back to our pool of wave functions. Maybe I should. So we are hoping, that we are basically capable of describing anything, like, quantum disordering, merons, whatever, loops of merons and so on. But what is maybe the, not shortcoming, but the way we approach things is that we take that there is a fixed number of particles in the upper layer and the down layer. So in some sense, we will settle for this first phonon correction where I have the same number of up and downs. And
Sorry, can you back up?
Yes.
One more slide. Oh, okay, this is go on. Sorry.
yeah.
I can understand.
So now the question comes, we look at our, you remember the class A, you have this 1-1 intercorrelation, you have your composite fermions up, composite fermion down, composite boson down, composite fermion up, composite boson, up. So, so you nucleate these composite fermions, and the first guess, and it might be quite obvious to you, this first column correction would be just nucleating and introducing one composite fermion down and one composite fermion up. So, now what is the wave function that will describe this? So we are missing this link between composite fermions, so-called, it's just some single particle here and single particle over here. We are missing this link between them. So in order to have in the form of the construction like some operators acting on the 1-1 state, and to have the electronic state, we will just symmetrize this link that is missing in this construction. So we will stay in unprojected approach, kind of Chern-Simons approach. So we will just plug in, describe this construction by these density operators, up and down density operators of your electrons. This is counting all up electrons and so on for the down electrons. And use translation invariance, and here we end up with some eta, which is complex number, just denoting these z's here. And we want to be more general and include that there is some pairing between composite fermions. So this we will denote by G. So G is equal to 1 if there is no pairing, but it's in no way S-way pairing.
So may I ask?
Yes?
So are you not moving away from nu equal to 1 with this wave function?
Yes. You have to understand that I'm describing always pool of the wave function. I don't know which the superposition would be correct, but certainly this is the first correction to the 1-1. So I would have 1-1-1 plus this first correction. And it will gain more important because of this factor D that you So this will be evolution of my ground state. It will start with 1-1-1, and it will introduce this first correction that we are now describing.
Yeah, so it seems to me, since you add this one over z minus z factor, that you slightly increase the density of the system, or the filling fraction.
No, didn't change. Didn't change microscopically. Maybe just a small change in the power that.
Yeah. Because you're not,
you will see that somehow that's not a good choice if you have just one of eta. So
because you're not adding a second flux quantum to make natural causes fermion.
No, I'm just having one. I'm calling composite fermion up and composite fermion down, but there is nothing special about the intercorrelation. This is just kind of density fluctuation here and density fluctuation there. So I'm staying with the same number of particles. I'm slightly changing the flux, but basically the choice that we made. So back to so we are just listing possibilities for this G pairing wave function. So if I have no pairing, first quantum correction in some way ill. It doesn't conform to the way we know from the first principles. If I take something of this in this manner, if my pairing function is of this in this manner, I would kind of heal this complex 1 over z, and I conform to the how should be with my superfluid, what phonon correction should be in the that we know from the Chern-Simons. It's 1/k. If my pairing function is 1/z, you know, it's like Pfaffian kind of 1/z or 331 Cauchy determinant 1/z. When you calculate this integral, simple integral, you find some delta function that after multiplying with the 1,1 state, you find that there is no correction, so no phonon correction. So you stay with the you would stay with 1,1,1 state if you would have this kind of pairing. This is all in the realm of possibilities. We are just kind of judging what could be the pairing function of our system. So it's more or less expected. I mean, if if 1/z would lead to some kind of incompressible state, you wouldn't have any correction of the phonon type. So your phonons are up there, gapped excitations, so that's somehow something that we would expect. So you can go on just making a little stronger pairing function. You still have, you neutralize that phase into 1/z that we had previously, and you end up with a phonon correction like this, which is kind of not the one that we expected for the Coulomb interaction. So it will just influence the Goldstone mode, will not be linear, so we don't expect in fact that we have some kind of pairing of this nature in the superfluid. So to have a behavior of a normal superfluid with a long range order, pairing among composite fermions should be in the reverse manner. So this is the kind of pairing that we, with our analysis, found out. Numerics indeed point out, that was Gunnar Steves and Andrzej work, indeed some kind of px plus ipy. So you know when it's minus sign, it's Pfaffian kind of case. But when you have reversed kind of pairing, it's the other way around, and it's that you have this star here, so it's a phase of star that we are talking about. So here is, so any more questions? So this is the third part. So we can imagine that somehow as we increase the distance, there are more and more composite fermions, they pair, and the outcome of this should be some paired phase of composite fermions. That's what we found out just describing and considering the disordering of the superfluid before. Now, all that we can say, it's various possibilities of pairing in the reverse manner or superposition of them. And we didn't include the lowest Landau projection, and for some time we will just stay in this language. So at the end of the day, you have your composite fermions up and down, and there is some kind of the pairing in the reverse direction. I picked up the particular kind, but any kind of px plus ipy pairing seems to, I mean, when I say that, I mean when for the short distance behavior we have this. So that's why we have the whole, this reverse manner pairing have so many possibilities, but they, as classification goes in the description as px plus ipy pairing. So let's stay with some particular case of pairing. This is Cauchy determinant pairing between ups and downs. So what is interesting, after all, with this kind of pairing is that we can describe this separating charge part and neutral part, that the simply neutral part has as description of holomorphic and anti-holomorphic part in the same way. So you can use 2 Majorana fermions here and 2 Majorana fermions here to describe your neutral part that is just 1 Dirac fermion. And either you will use this Cauchy determinant representation of the one of the vertex correlator in the non-chiral boson CFT. That's basically what you have. And this is more detailed description of your correlator. You find that your vertex has the exponent equal to alpha equal to 1. So then we can use this bosonic CFT to find out about excitations. We have a field, bosonic non-chiral field, and there is a dual field to it, to the same field, and look for excitations in the form of the vertex operator. When you insert this vertex operator in your correlator, CFT correlator, that is equivalent to these multiplying factors that multiply your pairing wave function. And alpha is equal to 1, you are bound to have delta 2 to be, for single valueness, that delta 2 has to be 1/2. But look, in the upper part, you can have the whole continuum of delta 1. So in the sense you expect, just by making the single valueness requirement, it seems you can continuously connect your excitations, can be continuously connected to the paired state, your ground state. And so the requirement for single valueness allows also a gapless branch. So this was just a small kind of digression that was telling you somehow, even with this paired state, you cannot hope for some kind of incompressible phase. It might be that you will still have some modified kind of superfluid, some kind of gapless state that somehow in translational invariant system develops after the this superfluid as we described before. So, but oops. So, anyways, I mean, we are talking about unprojected wave functions. We are not on the firm ground in the way of viable quantum Hall states. Let's look at this wave function. How we will project. The way to do it is, as you can maybe guess, is if I have determinant of z up minus z down. can multiply with the 1-1 state. And what I then get by applying the Cauchy identity, I have psi 2, 2, 0. So how we in this way we can insert 1-1 state in the z direction, and in the opposite direction some kind of charge, some kind of neutral insertion, which is shouldn't be somehow harmful or spoil our story of the determinant pairing, because charge insertion wouldn't change much, at least in the Chern-Simons description. So at the end, when you do these insertions, you end up with some wave function that looks strange, I would say, but this is the wave function. It's the wave function of the same shift as 1-1 state, but it has you have 3-3-1 state, and you act with the opposite flux, and somehow you end up with a similar state with the same shift, but with probably some different features than the 1-1 state. And certainly you can generalize this construction, and these are the so motivated construction where you take to the n equal arbitrary integer. But what is really hard about this reversed flux construction is that we don't have neither we have pseudo-potentials that can model the wave function, that the wave function is ground state, zero energy state of the model Hamiltonian. Neither we have root configuration to describe this state. So from the point of numerics, it's really hard. But I just want to show to you that they indeed should have some relevance to the problem of the reverse flux of the quantum Hall bilayer. You see, these are reverse flux wave functions. You're increasing the n, and this is just a system with 2 plus 2 particles. You shouldn't certainly take this as some kind of phase diagram or something, but the trend that you see the relevance of these reverse flux states. So we shouldn't really, it's case specific, and we shouldn't extrapolate to something like a large particle limit, but that's kind of some interesting result that can be basis for future work. So my conclusions are following. So a smooth transition to two decoupled Fermi liquid-like states at finite distance seems very unlikely. So when we try to nucleate these Fermi liquid-like condensates in the 1-1 state, what we found is kind of bad superfluid. So from that we can, the conclusion that we can make is that really at finite distance it seems that these states can, in the translation invariant system, cannot transform into decoupled Fermi liquid-like states. It's a different matter if we have disorder, and probably the cause for the nucleation of Fermi liquid-like condensates, and at some finite d, like in experiments, we have two decoupled formulated states. And the second, as you can see, that by assuming intercorrelated composite formulas in the superfluid ground states, their pairing must be in the reverse manner and are expected to make a paired phase in a translatory invariant system as a result of the disordering of the quantum pole superfluid. Thank you for your attention.
Questions? So in the previous slide,
Yeah.
I'm not sure if this means anything. No. There was that all these lines seem to sort of get very high overlap, but this distance over LB being 1. Do you have any?
Not at the moment. So you should go to somehow to higher. I think mathematically achievable is 3 plus 3 or something, but that's basically. At least we can get a clue whether it will stay like, as you said, that distance around 1, we have some kind of condensed, very high overlaps.
This is for Coulomb interaction.
Yeah, it's a Coulomb interaction.
Yeah, you mentioned a toric code-like effective theory. Can you explain it?
Oh. So basically, this is the wave function that I started with. So if I fix that delta 2 is equal to 1/2, and somehow fix that delta 1 is equal to 1/2, mutual statistics, as you will look at your correlators, will be semiotic, which is toric-code feature. So basically, the content of your excitations would be just as of the toric-code. Nothing, that we have effective theory of the system. That's one possibility is that paired state might be incompressible to describe to have effective theory of the toric-code, but that's because of this pairing in the reverse manner that we really know that is in the superfluid. So after all, you expect that something will occur in the pair phase after all, and the consequence of that is that one of the possibilities for the pairing in the reverse manner would be determinant, Cauchy determinant, as I explained.